So today we're going to talk about LeChatelier's principle. LeChatelier's principle tells us that if an equilibrium system is stressed, then the system will experience a shift in response to the stress that reestablishes equilibrium. And so the four different kinds of stress that we're going to talk about are a change in concentration, a change in pressure, a change in temperature, and the addition of a catalyst. So what do we mean by stress? A stress is any kind of disturbance to an equilibrium system. So you have a solution and it's there at equilibrium, minding its own business, and you add something or you change something so that Q is no longer equal to K. So the system is no longer at equilibrium. We can use LeChatelier's principle to predict which direction the reaction is going to need to proceed in order to get back to equilibrium. So LeChatelier's principle allows us to predict the relative magnitudes, which is bigger, Q or K. And when we know whether Q is bigger or smaller than K, we can know whether the reaction will go toward the reactants or toward the products in order to get to equilibrium. So what do we mean by a shift? In the case of a shift, we mean which direction where the reaction is going to go in order to get back to equilibrium. So the reaction could make more products, so we would call that a shift toward the products or toward the right, or the reaction could make more reactants, so we would call that a shift toward the left. So in this graph, we can see concentration as a function of time. And so we see that in the early part, the system is in equilibrium where there's some amount of H2 and some amount of NH3 and some amount of N2. And so if we add additional N2 is a reactant. In order for the system to get back to equilibrium, we need to move toward the products because compared to equilibrium, we now have too many reactants. And so what we see as as the concentrations change in the second part here is that the concentration of NH3 goes up because it's a product, and the concentration of H2 and N2 go down because they're reactants. So we would say that this reaction mixture shifts toward the products in order to re-establish equilibrium. So here at the new equilibrium at the end, we see that we have a new consistent ratio of H2, NH3, and N2. So let's talk about our four factors. The first is concentration. Concentration stress of an added reactant or product is relieved by consuming that substance. So in our last example, we saw that adding N2 would cause a decrease in H2 and an increase in NH3. So you see here that if we increase H2, that would also cause an increase in NH3. In our last example, we saw that H2 actually decreased because in order to decrease NH2, we also had to decrease H2. So concentration stress by removing a reactant or product is relieved by net reaction in the direction that replenishes that substance. So if we stressed our equilibrium in a different way, if we removed the ammonia from the mixture, then we would have to consume N2 and H2 in order to make more ammonia. So here's an example of how that might work. In the first test tube, we have a 0.1 molar solution of iron 3. If we add a solution of thiocyanate ion, SCN, we see that this system establishes equilibrium by making dark red FeSCN2+. This system is now at equilibrium. We can stress the equilibrium by adding, for example, a source of silver plus ion. Silver plus ion will react with some of the thiocyanate in order to make silver thiocyanate, which is a solid, and you can see the little cloudy white precipitate that's forming. So the addition of silver decreases the SCN in this equilibrium mixture, which means that in order for the system to get back to equilibrium, it's going to need to shift toward the reactants. So we're going to, in order to make more SCN, we're going to have to decrease the FeSCN in order to increase the SCN and the Fe3+. And the result of that is that we see the removal of the dark red color in favor of making more Fe3+. So next let's talk about the effect of pressure. There are 3 different ways we can change the pressure. We can add or remove the gaseous reactant or product, and so if we do that, that works basically the same as concentration. The next way we can change the pressure is by changing the volume of the container, either increasing it or decreasing it. And that's going to change the pressure because it's going to change the moles per volume. Okay, we'll talk more about that one in a second. The last way is that we can add an inert gas but keep the volume the same. That's going to increase the total pressure, but it's not going to change the partial pressures. So no change in partial pressure. And if it's not going to change the partial pressures, then we're going to have no change in Q, which means that we're going to have, basically the system is going to stay at equilibrium. So we should expect no change. Okay, so we can treat additions or subtractions of gaseous reactants or products the same way we deal with concentration. We'll talk about change in volume, and adding an inert gas at constant volume doesn't have any effect. We should note here that K, the equilibrium constant, is the same at all pressures for a particular temperature. So changing the pressure does not change the value of K. Okay, so here let's think about what happens if we change the volume of the container. So in this, so here we have a reaction at equilibrium in a container. We're going to decrease the volume by smushing it all down. And then we see that the number of molecules changes in response to that. So let's count them. So in this first reaction, we have 4 N2s, and we have 1, 2, 3, 4, 5, 6, 7, 8 H2s, and we have 2 NH3s. Okay, in this second mixture, we still have the same ratio of everything, 4 N2s, 8 H2s, and 2 NH3s, but then in the third mixture, the reaction has re-established equilibrium. And we now see that we have 2 N2s and 2 H2s and 1, 2, 3, 4, 5, 6 NH3s. So what we see happened here is that the reaction has shifted toward the side that had fewer moles. So if we increase the pressure by decreasing the volume, we're going to shift toward fewer moles in order to basically counteract the increased pressure. So you can see in the original reaction, we had a total of 14 moles of gas. And in this final version, we only have 10. We've decreased the number of moles of gas in order to relieve the pressure. So which side has fewer moles? We can see that on the reactant side, we have a total of 4 moles of gas, whereas on the product side, we only have 2. So since we increase the pressure by decreasing the volume, we're going to go toward the products. The reverse is also true. If we were to decrease the pressure by increasing the volume, so going in the reverse direction, we would see that our reaction mixture would shift toward more moles in order to counteract that change in pressure. So to summarize, if we increase the pressure by reducing the volume, that will result in a decrease in moles of gas, so we'll go whichever direction decreases the moles of gas. If we decrease the pressure by increasing the volume the other direction, that will result in an increase of moles of gas. And if we have the same number of moles of gas on both sides, we will see no effect. So try this yourself. What happens when the pressure decreases because the volume increases? Okay, so if the pressure decreases because the volume increases, pressure decreases, we're going to want to go toward more moles in order to counteract that. So the side with more moles here is the reactant side. So this reaction is going to shift toward the reactants. Let's consider the effect of temperature. If we consider heat as a reactant or a product, we can predict the effect of temperature. And so for an exothermic reaction, we can think of heat as a product. The heat is being released by the reaction. And so if heat is a product, then increasing temperature would be adding more heat. So that's like adding more of a product, and that is going to shift the reaction toward reactants, which means, remember that K is products over reactants. And so if we make more reactants, that is going to lead to a smaller K. So K will decrease. If the reaction is endothermic, we can think of heat as a reactant. We have to input heat in order to make the reaction happen. So in that case, if we increase temperature, then we're increasing a reactant. And so that's going to shift the reaction toward the products. And since, once again, K is products over reactants, then in this case, K will go up as temperature goes up. So how do we know whether a reaction is endothermic or exothermic? Well, we need to be given a value of delta H, or find some way of finding it. So here for this reaction that we looked at before, how does the equilibrium constant change when the temperature is increased? We see here that this reaction is endothermic because delta H is positive. So that means that we can think of heat here as a reactant. And so if we increase the heat and by increasing the temperature, then that means we're going to increase the reactants, which is going to make more products. Since K is products over reactants, then increasing the products is going to increase the value of K. So K will increase. We should note that only a change in temperature changes K. Changing the concentrations or the pressures just change Q. So our final factor is the addition of a catalyst. So a catalyst doesn't change the ratio of products to reactants. It only makes us achieve equilibrium more quickly. So as a result, adding a catalyst has no effect on equilibrium. And this is really important. We can't add a catalyst to make a reaction more or less favorable. We can only help it achieve equilibrium more quickly.